All right, ladies and gentlemen, let's go ahead and talk about this last step. So, you guys have gone through all the stations. You blew up your balloon. You messed with the syringe at station 2. You did not pop my bottle. In station 3 and at station 4, you watched me set up our experiment. All 4 steps, you have seen the 4 gas laws that we are responsible for. In the analysis conclusion questions, guys, this is what I want us to focus on. Using information gathered while at each station and the following variables. P standing for pressure, T standing for temperature, V for volume, and N for the amount. Because we're in chemistry, we're going to keep everything in moles. Write 4 equations for direct and inverse relationships between the variables. And do a quick sketch of a graph. So at station 1, everyone, each team got a balloon. As they blew into the balloon, what did the volume do? Did it go up or did it go down? It went up as well. If both variables go in the same direction, they're both increasing, I'm dealing with a direct relationship. So if I was to draw a graph, I'd expect to see something like this. As one increases, so does the other. Now, we are going to write an equation off of this. Because what it is that if we have, so in the beginning, you filled up a balloon with a couple bits of breath, and then you filled it up again. So you start off with a certain amount of gas in your balloon that gave you your initial volume. After you blew up your balloon, you got a new number of moles of oxygen in your balloon and a new volume. So basically it's a ratio. Now, I'm going to make this simple. This is not the equation I want you to focus on. This is how we set up our questions. Because a way to figure out your variables between 2 ratios is a process called cross multiplication, where I multiply my numerators and my denominators together. The formula that I want you to focus in on is N1 times V2 moles 1 times volume 2 equals moles 2 times volume 1. This is the equation that I want you to put in your head. We're going to put a bunch of names to these equations today. But I want you to see how we got that particular equation. At station 2, we had our syringe where we were pressing down the syringe. We were exerting force onto our syringe, pushing the air out. But as I pushed on the syringe, what did the volume do? It decreased. My plunger went down, leaving my air molecules only a few places to hang out, pushing them together. This is a indirect relationship. As one goes up, the other goes down. As one goes down, the other goes up. So if I were to draw this, I would see a downward facing angle. And because of this downward facing angle, my equation for pressure and volume is going to be P1 times V1 equals P2 times V2. That is going to be our equation. In a second, we're going to slap names to these. P1 is on the board right here. P1 times V1 equals P2 times V2. Temperature and pressure. Station 3. As my temperature increased, what did my pressure do? It increased as well. If they're both moving in the same direction, that's my direct. So that's my forward, my upward facing arrow. And we're going to see that all of my direct equations are going to have this pattern. 1, 2, 2, 1. T1 times P2 is equal to T2 times P1. Both of my direct relationships have the same pattern. 1 times 2 equals 2 times 1. My inverse, 1, 1 equals 2, 2. And lastly, at station 4, as I took my syringe and I placed it into my hot bath, what did the volume do? Did it increase or decrease when I put it in a hot bath? What did it do? It increased as well. So another direct relationship. T1 times V2 equals T2 times V1. These are my 4 gas laws that we are going to work with. In my 4 simple gas laws, changing gas laws, I'm dealing with only 2 variables. But soon, I'll increase my variables. And soon, I'll stop dealing with changing variables and start dealing with steady variables. So I want to put this on the pause. I want to put this on the back burner as I jump into our slides for today. We are going to be talking about kinetic molecular theory, KMT, and the ABCs of our gas laws. So you want to grab the piece of paper that has the table at the bottom of your page. As we talk about our kinetic molecular theories and how can the properties of gases be predicted using our kinetic molecular theory and our gas laws. That's what we're going to focus on today. And in order to do that, we have to make some assumptions. Kinetic molecular theory of gases helps us explain our behavior of our ideal gases. An ideal gas is our theoretical gas. It is our perfect gas. It is our 100% reaction gas.
When do we rate that?
That's up to you. You figure it out.
Right. Thank you.
Now, with our ideal gas, we have several postulates. These are our rules of our ideal gas. Our ideal gas is always going to be made of tiny particles. Our ideal gas is going to be in constant random motion. They're always moving in different locations. If they're in a container, they're bouncing off the walls of the container. They're going forward. They're going backward. They're going at angles. They're going in 3-dimensional spaces. They're also not only colliding against the container, but they're also bouncing off each other. Undergo elastic collisions. That means as one gas particle flies up, another gas particle flies up, they make contact with each other and they go in opposite directions. Elastic collisions just mean they bounce off each other. I'm pretty sure at some point, someone along the way, maybe you were in elementary school, said when you were dealing with bullies, what do you always tell them? I'm rubber, you're glue, whatever you say bounces off me and sticks to you. Your particles are bouncing off each other. They don't say that to y'all no more?
No.
Oh. Listen here, I'm a product of my time. Much like you guys will be a product of your time. And a big thing is that the average kinetic energy, that KE that we talked about last week, of the particles is directly proportional to the temperature of the gas in Kelvin. Now, we are not very familiar with Kelvin. Don't worry, we're going to get there today. I'm going to show you the easy way to get Kelvin temperature. The Kelvin temperature of a gas. And I'm hurt that the ancient wisdom of I'm rubber, you're glue did not get passed down through the generations. Well, because I see the weird S thing, and that was before my generation, but you know what we did right? We passed it down. Either some...
The 3 line, the 9 line, actually.
Oh, that is. The S.
Yeah. I don't know.
I messed it up, but yeah, that weird thing. All right, hey, look, I don't go to your arts class to make fun of y'all, so I don't know why you're coming at me like this, all right? I'll just put that out there. It has been a very long time since I've used the ancient S.
Hey, I know that.
Thank you, Jose. I'm giving you guys 30 more seconds, and we'll move on. 2, 3, 4, 5. So push that down.
Oh, my chest hurts.
All right, guys, moving on. If you didn't get it, you can always get it from your neighbor next to you, or you can pick it up from me after class. So, these should be familiar to you. We just saw them on our table at the end of our question, at the end of our, excuse me, gas stations. The 4 main variables that we're going to deal with in all of our ideal gas laws. P stands for pressure, specifically normal pressure. When I'm talking about normal pressure, I'm talking usually about 1 atmosphere. Now, here's the thing, is that we've been taught multiple ways to read standard pressure, normal pressure. We can also read it as 101.3 kilopascals. We can also read it as 760 millimeters of mercury. We can also read it as 760 torr. And lastly, we can also read it as 14.7 psi. In the questions that you are going to see in the next coming weeks, you will see it. Your pressure can be in any one of the 1, 2, 3, 4, 5 different scientific units. Mostly you will see them in atmosphere or kilopascals, but it's going to be on you to know these equalities. And for those watching at home or later, these are the equalities I'm talking about.
Yeah, I have a question.
T stands for temperature. Temperature has to always be put into Kelvin. Now, sometimes I'll give you degrees Kelvin. Sometimes I'll give you degrees Celsius. It will be on you to convert your temperature to degrees Kelvin. Now, and all you got to do is take your Celsius degree and add 273 to it. And that automatically gets you into Kelvin. Sir, are you okay?
I was breathing bad.
I'm sorry to hear that.
I'm not good today. There's a lot of chance that happened to me Saturday. Sunday.
What does the K stand for? The word
Kelvin.
Kelvin Klein.
Not Kelvin Klein. Kelvin temperature system.
Wait,
As in 0 being the coldest we could possibly think of in the universe.
why does Pascal sounds like a Spanish?
Well, because it's Latin, and Latin and Spanish. Spanish is derived from Latin.
Okay.
All of the Romantic languages, French, Spanish, a bit of Portuguese, all that comes from the Romantic languages. So, V always stands for volume. You guys are going to see it either in liters or milliliters. Now, you could also see it in different ways. You could see as 1 liter is equivalent to 1 decameter cubed, or 1 milliliter is equal to 1 centimeter cubed. These are 3s. But for most times, I'm just going to give you guys the volume in either liters or milliliters.
Deci. Or access.
And lastly, lowercase n represents the amount of gas, and that unit is always in moles. Now, here's the thing, is I know that you guys are absolute killing it when you guys have to convert things into moles. Excuse me. You guys can convert grams into moles. You guys can convert liters into moles. You guys can convert particles into moles.
Like, just changing the name. Whoa.
You guys know these. You guys spent all stoichiometry jumping across the moles. Sometimes, most of the times, I'll give you the units in moles. Sometimes I might just give you the grams of something or liters of something, and you have to come up with the moles of it. Remember your process. Differential analysis. Keep it bouncing around in your head, because we're not done with it yet. All right, we got about 19 minutes to the bell, so I'm gonna give it 10 more seconds. I'm gonna move on to the next thing. All right, we're moving on. Now, before I had you guys draw out your direct and indirect relationships. Now, direct relationship, as your x-axis increases, so does your y-axis. So a great example of this would be grades on a test. So grades on a test. It's my y-axis. And my x-axis is the hours I studied for said test. Now, I know that the less I study, the more likely I am to fail my test. But the more I study, the higher my grade is. Therefore, as one goes up, so does the other. This is my example of my direct relationship. My indirect relationship is going to be something like we see in econ. The price of an object is an indirect relationship with how easy it is to get. So basically the demand. And what we'll see is that something's really hard to get. Usually it's very pricey. But the easier it is to get, the lower it is. We are currently seeing this with our gas prices, ladies and gentlemen. If you don't know, I know a couple of us, a good amount of us are 16 to 18. So we are embarking on jobs where we have to drive now. You may be wondering why the money you used to have in your pocket is less than what it used to be, because gas is really hard to get a hold of due to a certain strait being blocked, but we can't say it because we're being recorded. And because it's hard to get, what happens to the price? The price goes up. But if I do the opposite of this, when I was younger, computers were very hard to get a hold of. They were fairly new to being household objects. When I was younger, they cost thousands of dollars. Today, you can go to Walmart right now and you can buy a laptop for under $100. Why? Because the demand for said laptop is greatly decreased. They're easier to get a hold of. Therefore, the price goes down. Indirect, as one goes up, the other goes down.
So the demand increase, the price of it too?
Mm-hmm.
Wait, what's that?
So, let's talk about the ABC gas laws. Avogadro, that's my A. Boyle, my B. Charles, my C. And then, now here's the thing, is that our last gas law is French. Now, I will tell you this. I'm terrible at pronouncing French names, so we're going to call him Gay-Lussac.
So,
I could be butchering the name. If you have a better interpretation of the name, let's hear it. If not, keep it to yourself.
Lusa.
So, Station 1 represented Avogadro's number, Avogadro's law, where as the number of moles increased, so did my volume. Boyle's law was Station 2. As my pressure increased, my volume decreased. Station 3 was Gay-Lussac's. As my temperature increased, so did my pressure. And lastly, Charles. Charles was Station 4. As the temperature increased, so did... No, sorry, not V. It's not P. So did my volume. So, Avogadro is a direct relationship. Charles is a direct relationship. Gay-Lussac's is a direct relationship. Boyle's is a indirect relationship. So here we have volume over my moles. Here we have volume over temp. Here we have volume. What is this? Over pressure. pressure over temp. These are our 4 laws that we are going to work a lot with. Now, when it comes to Avogadro's law, N1 times V2 is equal to N2 V1. This is the formula I want you to know. Do not worry about the 2 ratios equaling each other. This is what you are going to be using. Because you guys don't learn about cross multiplication anymore in Algebra 1 or 2. To make life easier, I'm going to tell you what you need to know. When it comes to Avogadro's law, this is what you need to know. When I go to Boyle, Boyle's my inverse. It's my weird one. P1 times V1 equals P2 times V2. That is my equation that I need to know. Charles, another one of my direct relationships. Therefore, I'm going to have that 1, 2 equals 2, 1. T1 times V2 equals T2 times V1. Notice that my direct relationships have that same 1, 2, 2, 1 pattern. My indirect has my 1, 1, 2, 2. One way to help us remember which one's which. If it's direct, 1, 2, 2, 1. Indirect, 1, 1, 2, 2. If my directs were 1, 2, 2, 1, for Gay-Lussac's, it's T what? 1 or 2? 1 times V times P, 1 or 2? 2 equals T 2 times P 1. Those are my excuse me. Those are my equations. Now, before we get out to it, I want you to grab this one right here. Gas laws, Boyle's, Charles, Gay-Lussac's, and Avogadro. Because I want to go over one question, at least one question before you get out of here. Because what you do not answer, the rest is homework. There's 12 questions altogether. So, make your life easy. Easy thing you could do is at the start of your paper is you could write down your laws. Write down those formulas. That'll help you out. Because our mixed practice, solve the following gas law problems. Show all work including equations and units. Round all to the correct number of sig figs. Let me show you what I want to see on your paper. Now I'm going to write really big on mine, so I'm going to run out of space really quickly. That's why I have the extra sheet of paper. If I'm looking at question 1, I have my question. I'm about to identify what law I used in my final answer. A gas with a volume of 4.0 liters at 0.610 atmosphere is allowed to expand until the pressure drops to 0.25 atmosphere. 250 atmosphere. If the temperature remains constant, what is the new volume? So, variable 1, 4.20 liters. Is that pressure? Is that volume? Is that moles? It's volume. That's my V1, right? 0.610 atmosphere. Pressure. My next variable, 0.250 atm. Is that pressure or volume? Pressure. I need to solve for volume. V2 is currently unknown to me. I want to see the variables written down. If I'm dealing with pressure and volume, which four laws am I using? Which one of the four laws am I using?
Boyle's law.
I'm using Boyle's law, right? So I'm going to write Boyle. I'm then going to write out Boyle's law, which is P1 times V1 equals P2 times V2. Now, I need to get V2 by itself. I need to isolate V2. We'll circle that because that's what I want. And I need to get rid of everything next to it. How can I get rid of P2? I'm going to divide by P2. Now remember, whatever I do to one side of my equation, I have to do to the other side of my equation. Now, very important, if I have the same number and variables in my numerator and my denominator, they will cancel each other out. I know P1 and P2 will not cancel each other out because P1 is 0.610 and P2 is 0.250. Meaning they do not equal each other. So I can rewrite my equation as V2 equals P1 times V1 divided by P2. So everybody see how I did that? Now, I have my variables. All I gotta do is plug and chug, right? V2 is equal to P1, which is 0.610 atmosphere, times my volume, 4.
An email access issue over the weekend and was unable to respond to after school and Saturday reset appeals. If you requested a change to your assigned day, you may attend any available reset session this week, Monday, Tuesday, Wednesday, Thursday, or Saturday. Please note there are no reset sessions on Fridays. All other appeals will be reviewed and responded to by Wednesday. Thank you for your patience.
So I plug and chug my equation. Now I'm going to multiply my P1 and my V1. So 0.610 times 4.20 gives me a number. Now I'm going to divide that by my denominator, 0.250. Enter. I have an unrounded number of 10.248 liters. Why liters? Because my atmospheres cancel each other out, leaving my only unit in liters. Is this my final answer? No. How many sig figs does my final answer have? 3. Is my 4 big enough to push my 2 to a 3? No, it's not. So it means my final answer is 10.2 liters. What I expect to see in your questions, variables, identify them. Equation, your original equation, how you modified your equation. Your plug and chug and your final answer. You don't have to show me where you rounded. I'm going to see where you rounded because you're going to put your final answer in the box, 10.2 liters. That's all you got to do for the other 11 questions. Come Wednesday with them done. I am expanding on what you do tonight and tomorrow with more questions because application requires repetition. I can't do one equation and be I'm the master of ideal gas laws.